Okay, so like I was saying, what is happening, or what happened as I took more breaths and used more than one breath at a constant rate. Okay, so we're going to assume that as I blew the air out of my mouth, it was coming out at the same rate every time. Every breath I took released the same amount of air. Let's assume that, right? I practiced and I trained myself and I recorded the data, and I guarantee that it was correct. Okay? So we said a couple of things that are changing. You said the volume, the pressure, the weight, the amount of breaths that I took, and the surface area. Anything else? The color, okay, the color of the balloon is changing. I can write that down if you want. What else?
The thickness of the walls.
The size.
The size, okay? So what would affect the size? Let's say that the shape of the balloon is a sphere, right? So what would be changing inside it that would cause it to change size? What does a sphere have? A radius. So do you think the radius is changing?
Circumference.
Oh my God, so now we got all these other words. So radius,
Diameter.
circumference,
Diameter.
the diameter. Wow, all of those things are changing?
What about air pressure?
What about air pressure? I think that's what they meant by pressure.
Is it up there?
Yeah.
Oh.
Is that what you meant by pressure, or is air pressure different? The same? Okay, cool. So what you can notice here is that this is an example of a related rate problem. Okay, so something is changing as something else changes. Over there on the screen. There you go. Thank you.
Wait, put it back.
Okay, so as I blew air into the balloon, all of those other things started changing, right? The volume of the balloon changed, the radius of the balloon changed, the circumference, the diameter, right? So one thing was affecting so many other things. Yes? Okay, so for example, if I had a turtle tank, right? Or a fish tank, right? Is the length, the width, and the height of that fish tank ever changing?
No.
No, it's constant, right? That tank is not growing, it's just there, right? Okay, what if I got water and I started filling up that tank? I'm adding what to it? I'm changing the what now? I'm changing the volume as I add water, right? Okay, so what would be changing as I add water? Would the length and the width of the tank change?
No.
No, but would the height of the water change? Yes, right? The height of the tank itself wouldn't change, but the height of the water would change. The water is like the variable, right? It's like the volume, right? I'm changing the volume also. And as I change the volume, something else that's changing is the height of the water that's in there. Do you understand? Okay, so one thing is affecting other things, but they're related to each other. The rate at which I fill up the tank changes, right? The rate at which the what?
Water rate.
The height changes, right? You understand? So if I put a whole bunch of water in there really, really fast, the height is going to change really, really fast, right? If I put the water in there really, really slow, like I open the water hose very little, right? So I'm changing the volume slowly, right? Then the height of the water also changes slowly. You understand? Cool? Alright, let me give you another example. So let's say I had, this is a pretend ladder. Let me move this desk here. Oops. Let's say that this ladder is leaning against the building. Yes? Okay. Does the size of the ladder ever change?
No.
No. Okay. What if my brother was on the ladder and I wanted to be really mean to him, because you know that's how brothers are to each other, and I were to start grabbing the ladder from the bottom while he's up there, and I start moving it, I start pulling it away, and he starts coming down. Ah! Okay, so now are some things changing?
I'll do that.
What would be some things that would be changing?
The amount of adrenaline in the
Height at
body.
which he's at.
The height, right? The height of the ladder is changing from the floor, right? And also what? The distance of the bottom of the ladder from the what? From the building, right? So that's changing, right? Okay, what else is changing? What shape does this form? A triangle, okay, so do you think anything regarding that triangle is changing?
The angle.
The angles are changing, very good. What else? The length of the legs, right? That would be like the distances we talked about. But there's something else that we could talk about. The area, right, of that triangle, right? So the area bounded by that triangle would also be changing, right? Yes? Would this area be the same as this area? Yes? Or no?
Yes.
Yes? Some say yes, some say no.
I don't know what to think.
You don't know what to think?
Because like, no.
Because maybe they would just switch like names, I guess like multiply one side by the other and pull it out.
Okay, so here's an example because the other class thought the same thing. So let's say we started off and the base was 10 and the height was 20, right? And then as I pull the ladder away, the bottom's going to get bigger, right? So the base can't be 10 anymore. Let's say it's 15, which is what I said there. But the height is going to be smaller, right? It's not going to be 20 anymore, so we're going to make it 10. Okay? So now when I multiply those times the half, I don't get the same answer that I got before. Okay. So does it affect it? Yes? Will the area be the same?
No.
No. The areas are different.
Unless the base is 21.
Okay? You got it? You got an idea of what related rates are? Yes? Anybody remember another word for slope?
Rate of change.
Rate of change. So if I say slope, is slope a rate?
Yes.
Yeah, it's a rate of change, right? Okay, so whenever we're talking about rates of change, we're talking about technically slopes, right? And we know that slopes are just what? What do we do to get slopes? Remember we talked about two rates of changes? What were those two rates of changes?
A-rock and I-rock.
A-rock and I-rock, right? Average rate of change and
Instantaneous.
instantaneous rates of change, okay? What did we do to get the instantaneous rate of change?
Slope of a tangent line.
We had to find a what first? Find a derivative, right? In order to find that instantaneous rate of change. The rate of change at that one point. The slope at that one point. The slope of a tangent line, right? Okay, so in these types of problems that we're going to talk about today, we're going to be working with rates. And the main thing that you have to remember is that a rate is simply a derivative. Okay, so make sure you don't forget that. Good? Alright, let me give you the notes so we can look at what we're talking about. You kind of have an idea of what we're going to be working with. And a lot of the problems that we're going to be doing are all going to be real world problems where we're going to be talking about things like that. So for the next couple of days, we're going to have a lot of fun. Nice word problems to look like, interpret, and use to solve the problem. Okay, you have to interpret them. I'm sending your guys with this row, okay? So first off, let's write a little bit about what I mean by related rates. I kind of gave you some examples, but let me give you a kind of a better definition of it, okay? So related rates is all about finding rates at which a quantity changes by relating it to other quantities whose rates of change are known. So related rates problems are basically all about that, what that says. Finding rates at which a quantity changes by relating it to other quantities whose rates of change are known. So sometimes in a problem regarding related rates, they're going to give you some information, right? And you're going to use that given information to solve for other things. Kind of like you always have done in any math problem that you've ever seen. except now that we're dealing with problems that are involving a derivative, and you have to understand what it's telling you. Sounds good? So the main thing here is to remember that rates are what? Derivatives. Okay, so in most of these problems, we're going to be finding derivatives, okay? And most of the time, it's going to be like it says here with respect to time, not with respect to x, like we have before. Okay, because here we're talking about something real. Okay, the volume inside the tank is changing with respect to what? To time, right? How long I pour water into that tank is going to affect the volume of the tank. You understand? So most of these examples will always be with respect to time. So anytime we get the derivative, we're going to have to remember that the notation will be d something over d what? dt, because it's with respect to time. So anytime you get the derivative of a variable and it's not time, you're going to have to put d, whatever that variable is, over dt. Cool? Right. So a lot of the problems that we're going to be doing will have words in them, and you have to be able to interpret the words and write down what it is that they're giving you. They're not going to straight up tell you dr dt equals 5. Okay, you're going to have to figure that out from the wording. So we're going to practice writing the notation and interpreting it, and hopefully writing it correctly, okay? So let's look at the first part. Well, so a couple of things you have to look out for is, are they giving me a rate, or are they just giving me a specific value? Like, are they telling me the area, or are they telling me the rate of change of the area? If they're just giving me area, then I just say A equals whatever. If they tell me the rate of change of the area, then I have to say dA dt equals whatever, because that would be the notation that would represent that particular rate. You understand? And looking at this one, what are they talking about? The area of a circle is what? Increasing at a rate. So what is that? 6 square inches per minute represent? The area or the rate of change of the area?
The rate of change.
Rate of change of the area. So I know that that has to be a derivative. Okay, so what would be the derivative that would represent the rate of change of the area?
dA over dt.
D capital A dt, right? That's the letter we would use in geometry. Equals, what would the increasing tell me that it is? Positive, right? Okay, so it's going to be a positive value. And what is the value?
6.
6 inches squared per what? Per minute. Very good. Remember that area is always units what? Units squared. How about the next one? What's this one telling us? The volume of a cone is decreasing at a rate. So what are they giving me? The volume or the rate of change of the volume? Rate of change of the volume, okay? So what would I use to represent that? dV dt. That's the rate of change of the volume. And what is that going to equal? Negative? Why negative? Oh, because of the word decreasing, okay. And then 2 feet cubed per second. Why is it cubed? Because anything cubed is volume, right? Okay, you're multiplying 3 dimensions. Excellent. Okay, be careful there. Alright, how about the next one? The student population of United is growing at a rate of 3 people per day. So what letter or what would you like to use for student population of United? U? So let's say D capital U over dt. It's a rate, right? So it's had to be a derivative. Equal what? Positive 3 people per day. And everybody wants to come here. That's you. Okay, how about the next one? The height of a tree is increasing at a rate of a half a foot per year. Is that a rate? Yes, that's the rate of change of the what? Of the height of the tree. So what do you want to use for that? dH dt, right? That's the rate of change of the height. And it's going to be increasing, so it's a positive value at half a foot, right? Per year. Easy? Okay, and do the last one. The water level in my turtle tank is decreasing at a rate of 2 inches per hour. So what do you want to use to represent the water level in my turtle tank? W? You just want to use H again.
I mean, we can put.
But it's the water level,
Yeah, so it's,
right? So that's talking about the height of the water,
oh yeah.
right? So this would be dH dt equals what? Negative, why negative? Decreasing, good. So negative 2 inches per hour. How come this wasn't inches cubed?
Because it's just like the level of
It's not the
height.
area?
It's just height.
They're asking for your height.
It's not the volume, right?
Yeah, sorry.
It's not the volume, it's just the height of the water. Very good.